Right. So now let's, to figure out how the change of the boundary condition, let's compute this integral once more. But now it's not a circulation, so it's integral along some curve, which is not closed. The best way to compute it is again switch to, for example, polar coordinates and choose the element of the circle as their integration contour. Then, as before, we will get phi over 2 pi r d theta, and the integral now will be simply phi over 2 pi times theta. So now the exponent of this exponential will simply become e over h bar c phi over 2 pi times theta. Well, let's call this prefactor alpha, and this alpha can be expressed as follows. It's phi over phi naught, where phi naught is so-called flux quantum. It's 2 pi h bar c over e. Alpha is not necessarily integer, so because always the total flux can be quite arbitrary. So now our change of variables of wave functions looks as follows. It's e to I alpha, this ratio of flux to the quantum flux, times theta, times psi small. So in order for the psi capital function to be periodic in polar angle theta, this psi small function should be so-called semi-periodic, meaning that psi of r0 should be equal to e to minus 2 pi I alpha psi of r. So, and finally, with the help of this gauge transformation, their magnetic field will be absent completely from our Schrödinger equation, and it will be turned into a standard Helmholtz equation, where k squared is simply 2me over h bar squared. Now we use standard technique to solve the Helmholtz equation. The only difference from the usual case is that our psi function has this quite special semi-periodic boundary condition. So what we do, we expand psi function into a complete set of eigenfunctions. Namely, we do it like this. So it's e to I nu theta times psi nu of r, where nu is some full set of specially chosen parameter. Now let's recall the representation for the Laplacian in polar coordinates. Well, initially the problem is three-dimensional, but obviously the vertical axis is of no importance, and only transverse motion in x and y coordinate plane matters. And hence we can always split the motion into the motion along z-axis, which is of no interest, and the transverse motion. Hence, here I will use purely two-dimensional value expression for the Laplacian in polar coordinates, which looks as follows. As a result, when we plug in this decomposition into the original equation, what we do is a very simple sum. So it's e2 I nu theta, and here partial derivatives are turned into full derivatives of psi nu function, which are the functions of only radial variable, and here is the result. Psi prime prime. Here by prime I mean the differentiation with respect to r, plus psi prime over r. And finally, we arrive at the equation for the radial component of our wave function, which is a simple Bessel equation. Now let's see what the allowed values of this new parameter should be. According to this boundary condition, e2 I nu times 2 pi should be equal to e2 minus 2 pi I alpha times e2 I nu times 0. So as a result, nu should be equal to some integer m minus alpha. So slightly unusual. In most cases, when we require the single valuedness of our wave function, nu are integers, and this leads to the quantization of momentum of the particle. Here, the situation is slightly different. So, and the solution of our radial Schrödinger equation is simply the combination of two Bessel functions.